Hello, everyone. Thank you for reviewing my presentation today. My name is Brekke Slyke. I'm a master's student in the Mechanical Engineering Department at the University of Idaho. I'm going to be presenting to you a case study I did doing a techno-economic and environmental assessment of dairy products based in southeastern Idaho. I'd like to start out with a simple overview of this project. The motivation behind this case study was to examine the environmental impact of dairy processing. Specifically, I was interested in looking at the manufacturing environment and processing conditions for dairy products. I wanted to see if changing basic processing conditions could reduce the environmental impact without increasing costs or interfering with production. I'd like to give a little background to this. So a little background on the dairy industry. The dairy industry is quite large, and in 2019, the United States production of milk was approximately 218 billion pounds of liquid milk. Idaho produced 15.5 billion pounds in the same year. Production and consumption of milk and its various derivative products is large in the United States and continues to grow. In recent years, dairy manufacturing has experienced a trend of moving from lots of smaller plants into large plants. This trend toward large-scale manufacturing increases the environmental burden the plant has on smaller areas. It increases the impact of the liquid waste disposal, noise, and gas emissions in the vicinity of and/or because of the manufacturing plant. In order to create my case studies, I created a computer model of a typical dairy processing plant using ASME software. Creating a model using this software allowed me to test alternate processing conditions while still keeping the essential processes and temperature requirements in place to produce a sellable product, in this case, liquid or market milk. The model also allowed me to investigate the production process using an exergy analysis of the different parts of the process. Using an exergy analysis allowed me to optimize portions of the process that were wasting the most energy. After optimizing the production conditions, the model was run again, and the typical or common conditions, or what I call the base case, was examined and compared to the resulting optimized or proposed case based on the environmental and economic impacts of the process. The environmental impact was examined through a life cycle assessment. The life cycle assessment was set up as follows. My goal was to look at the global warming potential for a 50-year period based on the greenhouse gas emissions. This was a gate-to-gate study. I did not look at the impact of the dairies or transportation of raw goods to the manufacturing plant, nor transportation of finalized goods from the plant, nor the final life of those products. Essentially, my scope is the midstream segment of the dairy products, specifically the liquid or market milk product. The functional unit I used for this study was 1 kilogram of carbon dioxide equivalents per kilogram of packaged milk. For the life cycle inventory and life cycle impact assessment, I used information from a variety of open sources and databases. As you can see from the right here, open source, life cycle, OpenLCA, and EcoInvent. There were multiple inputs included into the process, such as raw milk, water, electricity for plant services. These could include things such as the HVAC, cleaning, lighting, storage, refrigeration, and heating needs, and whatever was needed for the process itself, heating oils, container resin, which was soon to be HDP. I don't know the word. I'm not going to try and spit that one out. Diesel for transportation. There's two main processes in dairy production, which is the raw milk processing and then the packaging processing. Raw milk processing essentially has 4 steps, which is receiving, separation, homogenization, and pasteurization. Packaging process is container formation, filling and storage, and then transportation in and around the plant. As I said, if you're tending toward a very large plant, product has to be moved around. Outputs, of course, are milk. If you're doing liquid milk, you'll have small cream side product, heat loss, and greenhouse gas emissions. So for the assessment, I had to compare a current process to a proposed process. As this was a modeled process, I had to set some conditions and the assumptions for the model to work. Part of this, of course, was assuming a location, which was as stated before, was Southeast Idaho. The process was set to maximize production of market milk, in this case, liquid milk, as that's very straightforward product and doesn't require a lot of extra processing. And there was no optimization of the packaging process for the proposed cases. So my focus was, as you can see down here on the left, the raw milk processing. Raw milk processing, essentially, as we said before, was 4 steps: storage, separation, homogenization, and pasteurization. Homogenization makes sure that cream is put back into the product and doesn't come out. Pasteurization ensures that it's safe for consumption. However, in the past, as these dairy processing plants were built, there was a trend to try and use energy and reduce costs and use energy efficiently. So all 4 of these steps, although they go one right after the other, are essentially connected in a complex way by a large-scale heat exchanger. This can make the energy usage and heat transfer relationships between the 4 steps difficult to understand, which is why I ended up using an exergy analysis to try and find the best places to optimize it. When looking at the economic assessment, I used a life cycle costing analysis method, which essentially had a net present value, payback period, and total profit, on which I compared the base case and proposed case. Once again, assumptions had to be used. In this case, when I built the model, I created a mid-sized plant, which had a production rate of 10,000 kilograms of packaged milk per hour. I assumed a production schedule of 300 production days per year and only a 20-hour production period per day. This is because there are extremely important sanitation requirements for the production of milk. And so they will experience multiple shutdowns in a production period during a day for cleaning. And in addition, most food plants, dairy industry included, will have an annual shutdown of around 2 weeks a year to do deep cleaning and major equipment repair or replacement. From our figure over here on the right, there were several costs that were considered to be constant across the cases. These were things such as the original build of the plant, the demolition of the plant, its annual operation costs, packaging material, raw material costs, things like that. However, the biggest difference that was put in place is variable costs. By changing the operation conditions, you end up using more or less wastewater, in this case less, as you're doing your processing. Your cooling needs are reduced, your electrical costs are reduced, your heating costs are reduced. So these were the data that was generated through the model and then was used for the assessment. Moving on to the results, the greenhouse gas emissions for the 2 cases were compared for both cases based on whether it was the base or the proposed case, but also based on the heating system power source, having either an electric only source or having a natural gas fired boiler. In this case, I used both of those because both of those are in common use in the dairy industry. Coolers, which are also needed in this process in the dairy industry, are almost exclusively electric. So they were not compared based on that. So as we're looking at our figure, you can see, although the cooling costs were reduced between the base case and the proposed case, there was no comparison between electric or fuel in this case, natural gas. However, for heating and electric, you can see that there was differences between heating with electric or heating in fuel, how much greenhouse gas emissions were generated. These numbers are in kilograms of carbon dioxide equivalents per kilogram of packaged milk produced. So these three, and then of course there's the total electric and then the total fuel costs. There's some standard costs across, as I said, refrigeration is standard across both, packaging costs are standard across both. However, what ultimately came out of that is the electric systems resulted in approximately 13% less emissions than their fuel counterparts for this study. Optimizing the conditions reduced emissions up to 6.4% simply by optimizing the heat transfer process. Looking at the process from the economic impact viewpoint, this was actually a little bit different. In this case, using the fuel dropped the heating cost to the lowest cost contributor. As you can see, between comparing the variable costs for the base electric case versus the fuel case, especially once we put in the optimization, the heating fuel needed for the process reduced immensely. Overall optimization of the heat exchanger process lowered cooling and heating costs regardless of the energy source used. So in either case, whichever one the plant is currently using, being able to optimize their heat transfer process will reduce, obviously, their operating costs, but it also will reduce their emissions. Looking at some of our conclusions as we did these case studies, several things were observed. First of all, in the manufacturing plant alone, the energy consumption required for processing contributes 41% of the environmental impact of the plant. So all of these case studies generated between 0.0102 kilograms of carbon dioxide equivalents per kilogram of packaged milk at the most optimized, most economically friendly option to 0.0125 kilograms of carbon dioxide equivalents based on what was the essential base case. Obviously, from the environmental standpoint, the electric-based proposed case study reduced the most greenhouse gas emissions. However, some of that is because of where this study was based. Obviously, I based the plant in Southeast Idaho, and in Southeast Idaho, most of our electric power is from hydroelectric dams. And because of that, the emission factor used for the calculations was nearly 20% less than the national average. So had this study been based elsewhere, it's quite possible that the electric case would not have been the best environmental case. In the economic drivers, one of the biggest drivers was the heating and cooling costs. Optimizing those reduced the cooling costs, but it had a huge effect on the heating costs. So the proposed case produced an 84% reduction of heating costs. And overall, over the whole the whole production process, it was able to reduce 16.3% of the annual variable costs by optimizing the heat transfer process. There are areas for further study and further investigation. One that could be included is by looking into, rather than electric or an electric or natural gas fired boiler, to be looking at biodiesel or biogas fired boiler for the plant. Depending on your area and if you have a setup for it, that might help reduce further emissions. An additional area that can be looked at is looking at the effect of the transportation section, which wasn't included in this, and the environmental impact based on the actual geographic location, and how much the location affects the impact is another area that could be explored. I'd like to thank everyone for listening today. I'd like to give a special thanks to the University of Idaho and the College of Engineering for their resources and facilities. As this is a recorded presentation, I'm unable to address questions from you right here. However, if you do have questions, comments, or feedback, I encourage you to contact either Dr. Brekke or myself at the emails that you can see here below. This is Dr. Brekke, and then Vans with all of the 8s in front of it. That's my email. Please feel free to contact us with any questions or concerns that you might have. So once again, thank you all for your time today, and I wish all of you a wonderful conference.